Hi everyone, good evening guys. Welcome to the third session in Master Series. We are doing linear regression as you have been aware, right? I know most of the guys must have gone through the session one and session two. And just give me a second, guys. Yeah. So let me quickly do a recap of session one and session two. So we started with simple linear regression, right? And we started giving a full idea about the machine learning, and then we got into the simple regression, linear regression model, right? We started with the intuitive idea about it, right? And why do we need it? So as you can see here, we were talking about in session one, intuitively, if you try to fit a blue line, right, to the orange data points, which are the circles, right? Idea is to minimize the sum of squared residue or error, as you can see on the right hand side. And the red line is coming from the best fit line. And then we got into uh, the the mechanism behind the minimizing the residues, right? And there we introduced OLS, which is very famous, ordinary least square method. This is one of the techniques that we use to minimize the sum of square errors and get the best fit line. Then we got into the derivation of it, uh, how we can derive beta naught and beta 1, as you can see on the screen. Yeah. So if you see here, we started with our error function, which is sum of squared error. And then the idea was to minimize this error. So what we did, we took alpha and beta and differentiated with respect to alpha and beta using the concept of maxima minima. Here, idea is to minimize the S function. And by doing that, we are able to calculate alpha equal to yi bar, which is mean of yi minus beta times mean of xi. And when we did, del s by del beta equal to 0, and then we found beta equal to, it's a big lengthy equation. So it is n sum of product of xi's, yi's minus, sum of x into sum of y divided by n times sum of x squares minus, square of the sum of x. So yeah, these are the ones, these are the ones we have to calculate. Once we have alpha and beta ready, we can actually calculate any linear regression model coefficient. Make sense, guys? Any question so far? I'm looking at the chat. Yes, no? Okay. So now, agenda for the session three. Before we get into the agenda for session three, let me quickly reiterate uh, that what's the whole intent of doing this, the masterclass series. Hold on. Yeah. So if you see on the screen, just to introduce this to the new learners coming on the channel, that GATE has introduced a new paper. This is going to happen 2024 onwards. This is the first time GATE has come up with a new paper on data science and AI. They are calling it DA paper. And this is a golden opportunity for everyone who is trying to, get a career in data science, rather than doing some boot camp and some diploma kind of crash course kind of training. You can actually write a GATE paper in data science and do masters from top colleges like IITs, NITs, and then you can have a fulfilling career in data science. So that was the intent to, bring master series to you guys. And those who are interested in the program, as you can see on the screen, uh, there are a few links which you can click and get more information about the program. So for the live online program, you can click here. Uh, for the classroom program, you can click below the link, in the below link. And if you are planning to join any group, you're looking for some Telegram, WhatsApp group. So what you can do, you can click on this link and join it for the latest and greatest updates about GATE DA paper. Okay, cool. So now let me, excuse me, go to the session three. So in session three, our focus would be to introduce key terminologies in linear regression. These are broadly known as sum of squares, uh, and it is SST, SSR, and SSC. Sum of squares total, sum of square error or residue, sum of square regression. And once we have gone through these sum of squares, we can bring it coefficient of determination, which is really a good measure for linear regression, right? It helps you to understand that how much of the variance in x is being explained by the target variable y. So very, very important measure. Once we are done with that, we'll give a quick uh, uh, view to the shorthand notation for linear regression formula, given that you have seen the formula for alpha and beta, and it is really lengthy. And then in the end, we'll try to do demonstrate linear regression with a real data using Excel. Make sense? Sounds interesting? Okay, so what is sum of square is going to give you, right? So if you recall a bit of statistics or the fundamental statistics from your school days or engineering days, right? Generally, when you do sum of squares, it represents variability in the data, isn't it? So if you look at the variance, if you look at the variance formula, so if you find variance of x, how do you find variance of x? To get into variance of x, what you do, you subtract mean from each exercise, take a square of it, sum total it, and divide by the number of data points. So if you look at the power here, this is what I'm trying to say, sum of square. So in linear regression, we have three key definitions to understand the different variability explained by the linear regression model. Generally, sum of square indicates dispersion of data points around the mean and how much the dependent variable deviates from the predicted values in regression analysis. Make sense? So to make it simple for us, what we do, we decompose, let me write here, we decompose, we decompose variability to understand the sources of variation in the data. To understand the sources of variation in the data. That's number one point. To assess a model's goodness of fit, that would be number two. And understand the relationship between the variables, isn't it? So this might look a little overwhelming at this point, but let me get into the diagram, right? If you focus, you will see that what we are trying to show, and please be focused on my cursor and try to not jump, don't try to jump into the formula and all, since it's a it's a complicated diagram, and thanks to the guys who have put together this, right? If you see here, what we are saying that these are your data points. So let me say all those which are black circles are your data points. Let me share it to make it more visible on the chart, right? And if you focus on the one which we are trying to draw a line, vertical line drawing from the top of the data points till the linear regression line. Where is our linear regression line? This is your linear regression line or least square line. We also call it as least square line. So if you see here, we are drawing vertical uh, line from the data point to the line itself, and this is known as your sum of squared error. This is how much far your data point, actual data point, is from the regression line. And if you see the below one, which is we are calling sum of square Regression, right? That is your that is your delta between the actual value and the average value. Can you see there's a dot 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 line? So this is your average value and the actual value. Okay. So this average value is coming as the average of the target variable. Can you see this? This is y bar. Okay. And overall, if you see sum total this, which I mean to say the difference between the uh, actual data point and the average value. So this is your actual data point and the average value, that becomes your sum of square total. So you have actually regression sum of square, which is the difference between the average value and the predicted value. Okay, this you have sum of square error, which is the difference between sum of square error is actually the delta between the actual data point and the predicted value, and the total is difference between the actual data point and the average value. Okay, so the terminology can be a little bit tricky, but if you see that we have defined different variability for each of the measures. Now, if you look at that mathematics, this is what we are saying, that SST mathematically can be written as sum of square error plus sum of square regressions, right? Or regression sum of square. So there are different ways to call it. Make sense? I'll take a pause here. Any question, Shivesh? So far, so good. Now, let me give you quick pointer that what is SST? SST actually depicts total variance, right? That's why it is called total. Of what? Of Y. SSE, right? SSE is the variance that cannot be explained by the regression line, right? That's why this is error, regression line. So some of the variance can be explained by regression line. Some of the variance cannot be explained by the regression line. Total, if you do, it becomes your total variance. Make sense? How much you can explain by regression line, we denote by SSR. So we can say, this is the variance that can be explained by the regression line. So now I'll go into one by one all of those mathematically so that it makes a lot of sense. So let's put the heading, total sum of squares, and let's double click on it. Okay. So guys, we are trying to demonstrate how do we run session in our program, right? So already we are almost 1 month into the program, which is more like a training program for GATE DA paper, and this is how we run the sessions in the class. So I'm not showing any slides, or I'm not giving you uh, any all printed material and showing on the screen and just writing nothing. So that's where you might feel that we are going a little slow, but that's the whole idea. Given that engineering guys don't have a lot of background in data science, and it can be a bit overwhelming for those who are seeing for the first time, to make them comfortable, we have to go slow. We have to understand nitty gritty of each and every topic, right? Makes sense, guys? You agree with me? Give me a thumbs up if you agree with me. Yeah. So now let me give you the formula for this one. So already, if you look at here, uh, SST, or sometimes we also write it as TSS. What is this, guy? This is the delta between, and you can see the formula is written on the top as well. Yi minus y bar, right? Yi minus y bar whole square sigma I equal to 1 to n. So now what is yi? Yi's are the, right, actual y values, right guys? Come on. What is y bar? It's the mean of y values, right guys? Correct. So if you find each and every value and subtract it, subtract the mean from these values and take the square and sum it up, that becomes your SST. Guys, SST, if I have to write, it is a measure of, excuse me, it is a measure of the total variability of the data set, right? Cool. Now let's go on and discuss about sum of square error, which is SSE, sum of squares error. So if you look at the mathematical formulation for this one, the formula says SSE equal to SSE equal to is, you will subtract, and now the formula is on the top as well, yi minus yi hat, right? Although even if you do yi hat minus yi, uh, it doesn't change because there's a square there, right? So you're not worried about the sign as much. You will be when there is no square. So this is your, you're subtracting the predicted value from the actual value, as you can see on the screen on the top. So this is your predicted value and you're subtracting from the actual value and you get the residue here, right? So this residue, right, if I highlight, in this case, residue is positive. Guys can see that residue or error is positive. For particularly for this case, you tell me if you do, yi minus yi hat. So here it is positive. Here it will be negative residue. Agree, guys? And if you remember in session 2, I was explaining that why, or I think in session 1, I was explaining that why do we need to do the square of these residue? Because if you just directly add it up, it will cancel each other and the error will be uh, captured incorrectly. Okay. Now, if you look at SSC, this is your formula. And SSC means what? Let me write. It shows the unexplained variance, right? Unexplained variance by regression. And the last one is what? Regression sum of squares or sum of square regression. You can call both the ways. Uh, I'm looking at the chat, guys. Regression sum of squares. So I will keep switching my screen to look at the chat. So regression sum of squares or SSR can also be called sum of square regression. If you look at the formula, it is what? Come on, guys. It is the difference between what? Look at here, yi hat minus y bar, right? Yi hat minus y bar whole square I equal to 1 to n, correct? So you are trying to, subtract the mean from the predicted values, right? That's what we're saying there. Look at this. Agreed? And what does this tell to you guys? It is a measure of which describes how well our regression line fits the data, right? You can also say that it actually quantifies how much is the goodness of fit. And R square, when we'll be discussing about R square, which is coefficient of determination, which is a measure of goodness of fit, is going to bank on SSR and SST only. Make sense? Make sense, guys? Now tell me one thing. I'm putting a question there. What's the relation between SSR and SSE? What's the relation between SSR and SSE? What do you guys think? See, we know that SST is equal to SSR plus SSE, but what is the relation between SSR and SSE? Anybody in the chat? Excuse me. Come on, guys. Both are inversely related, right? Both are inversely related. So basically, what I'm saying that if you increase the sum of square regression, SSE is bound to come down. Correct? Right? If you are saying the total variability is what? Let me give one liner and then I hope you will be able to understand what I'm saying. Let's say total variability is what? Explained variability and unexplained variability. That is the sum. Suppose your variability is 100%, you are able to explain 70%, 30% you are not able to explain, total is 100%. If your explained variability increases, let's say, so this is your SST, this is your SSR, and this is your SSE, right? If your explained variability increases, focus guys, focus, then eventually SSE will come down now. Hello? Make sense? I'll take a pause here, guys. Right? That's the relationship. And I can also show this with some examples with a data point. So let's say if I, quickly take one simple x-axis, y-axis, right? And I just take some data points like 1, 2, 3, 4, and 5. Now trust me, if I draw a line, if you draw a regression line passing through, right, this data closer to this data point, right? So when you're looking at, guys, hold on. Yeah, I think my OneNote crashed. Yeah. So if you're so close, look at this example, particular example. Tell me what is the SSC here? Just talk about one data point. What is SSC here? Come on, guys, please ping in the chat. I'm having so many people in the chat. Anybody can quickly tell me. What is SSC? You will see that SSC, since the line is passing through the data point, SSE will be 0 and SSR will be 100%. Right? In terms of percentage, let's talk about it. Guys, and this is just for this data point. Don't get me wrong. Specifically, say this data point is 5th, 4th, 3, 2, 1. Only for 5, can I say that? So as you go closer, end of the day, it has to be total 100%. Agreed? Okay. So that's what, sum of squares tells you, right? And there are few commentaries that I want to give. So if you are having a higher SSR, means sum of squares regression, it suggests that a larger portion of the variability in Y is explained by the model, right? Suppose you are having a higher value for SSR compared to SSE. On contrary, if you have a higher SSE, which is sum of square error or residue, it means that your model is going to give you low accuracy, right? Because chances are very high that it is not going to capture even a significant variance in the data. So there will be quite a lot of unexplained variance, that would attribute to the lower model accuracy. Make sense? That's the interpretation here. So what we really want, we want to go as closer to the data point that will ascertain two things. Number one is that sum of squares regression will improve, which is basically means your goodness of fit for the line is higher. Your model is able to capture more variance in the data, and your SSC will come down because they are inversely related. So SSC will be like lower, so your model accuracy will be improving. Make sense? Can we draw a line here that okay, we are done with these squares of regression, sum of squares regression? Now, if we are done, let me put another heading, and that would be coefficient of determination. Coefficient of determination, also called R squared, and the representation, the notation is R squared. Now, coefficient of determination is a measure that provides information about the goodness of it, right? So you're actually working on a model, and you want to understand that how well my linear regression line is fitting the data point. So that can be quantified with the help of R square. In the context of regression, it is a statistical measure of how well the regression line approximates the actual data. So think, let's take an example. Suppose you are trying to predict number of sales for, let's say, any product X, and you want to do some advertising, right? We are living in the world of digital marketing, and in the end, we'll try to demonstrate one real data to show you that what is the impact of advertising. Nowadays you're watching World Cup, and you might be seeing a lot of sponsors, brand sponsors are coming and doing their ads in the middle of the breaks, right? Every over there is a break, right? One over to another over. So they will do, play a quick ad for 30 seconds, 20 seconds, depends on their sponsorship money. Now they want to measure the impact of ads on the sales. Let's say they are selling product XYZ. So now when we say that our coefficient of determination is high, let's say 80% or 90%, it basically means that your model is getting quite a lot of insights from the data, the actual data. And what is the data we are talking about? The data we are talking about, that let's say you are doing, let me put a columnar structure here, guys. So there are only two columns. You are looking at the sales. So let's say you are doing certain sales, number of sales, and you're doing ads on the TV. Ads on the TV. Suppose you do, let's say, X number of ads, and you are doing Y number of sales. X becomes your input variable, Y becomes your output, right? The target. So then you will be able to capture quite a lot of information, insights, and pattern from this data. So basically, it means that when you are trying to give unknown data to this model, that's the whole point of doing linear regression. Let's say I want to understand if I do, X number of sales later, or let's say that X is different from the original data, what could be my predicted number of sales, right? Is it worth it even? So let's say if I'm planning to give a bigger number of ads across different regional, cinema, regional languages, right? I'm doing the TV ads for almost 28 states in India. I would like to assess before I go and give this to, the other channel operators, that are we going to get that many sales if we run, let's say, 200 ads or 50 ads, right? Depends, in a week. So that's the whole point of doing linear regression. And if your R square is higher, guarantee of your model, picking the right number of sales increases, the chances increases. Since it's all probabilistic, we cannot put a number, we cannot put a point to that. Okay. So now, if I can give you the quick screenshot to save our some time, let me put it here. So this is how we define coefficient of determination. And now this is the formula we are going to use. So one of the way of calculating coefficient of determination is what? 1 minus sum of square regression divided by total sum of square SST, right? See? So 1 minus sum of square regression, total sum of squares, right? Okay, clear guys? Are we clear on this? I think, just give me a sec, guys. There's one. Yeah, correct. So I was just quickly validating, the formula. Okay. Now we already know the formula. We can get into the discussion, right, when we have a real data. Now let me interpret the result for it. Suppose you say R square comes out to be, hypothetically, R square comes out to be, let's say, 0.60. In percentage, it is how much? 60%. What is the interpretation of this? Anyone? Can you write in the chat? What is the R square 60% means? It means, guys, that a linear regression model or least square line model is able to explain 60% of the data set variability, which is y, with the help of with the variation or help of variation in x. So in simple English, if I have to say that it explains 60% of the variation in y, if I can write a simple one-liner, 60% of variation in y is explained by variation in x. Simple one-liner. So how much we are not able to explain, guys? We are not able to explain 40%, which would attribute to the error for the model, right? Make sense or not, guys? Clear? Now, if you want to understand R square a little more, so let me show you some amazing charts on the screen. So let me bring some charts from my secondary screen. And if you see, guys, here, what did I say? Independent variable x and dependent variable y on the y-axis. If you can see, you will observe that all the data points, the reds are your data points, right? Actual values. And the black line means your regression line. That's a lesson for the chart. If you're observing closely on the screen, you will see that the line is passing through all the data points, right? Which means that if you do that R square calculation for this particular data set, it will come to 1, or you can write 100%. So basically, what is the interpretation of this? It means that your model is perfectly captures everything, every variability in y with the help of x. Simple. So all the variation in y is accounted for by the x values, which is generally an ideal case. Means if you are seeing this kind of scenario in your model, you should doubt it. So model is like overfitting, and these are some jargons: overfitting. Uh, but for the time being, you can just note it down. So overfitting model is definitely suffering from overfitting, and that should not happen. You should investigate your model more. Now, moving on to the next example, right? If you see here, now the line which is passing through these data points are not actually all of it, right? So if you see that some of the data points are a little on the left, on the right, for example, this guy, right? It has some residues. If I drop a vertical line, see some errors are here. Only few data points are on the line. So basically here, if you estimate the R square, it will not be perfectly 1, but it will be closer to 1. And if I have the numbers, it is 0.83 for this particular example. or 83%. Means out of 100%, you are able to explain how much of the variance, guys? Only 83%. So 73% is unexplained and we are not able to capture it. And last but not the least, there can be another example. Let me show you. Now, in this particular example, guys, if you see, independent variable x is like and dependent variable y. If you look at the scatter plot, the actual data points are like far away from the regression line. You can see, and they're not giving you any obvious patterns in the data, right? So which basically means that if you do the R square for it, it shows that model is not going to give anything. 0% of the variance is explained or accounted for by the X values. Any question, guys? Quick questions on this? No questions? Okay. Now, once you have gone through the approach, you can find R square in this manner. So what you can do more about it is that, you know, uh, you can relate. There's a relationship between the correlation coefficient and the R square value. So what we are going to do, quickly walk you through, Pearson's, must have heard it or must have done it, correlation coefficient. It's a very important topic for linear regression as well. Uh, Actually, correlation coefficient is denoted by rho or R. And if you do R square, right, it will become the typical coefficient of determination, right? So that's where one way of calculating R square is what? You go and apply the formula, which I have given here, right? Or what you can do, guys, you can calculate correlation coefficient and square it off, right? So if I quickly define, correlation coefficient is, so I'll also do the commentary and write to, save some time. R is directly related to the coefficient of determination, which is R square in an obvious way, right? And R can be written as plus minus R, right? Let me put in a nice box, okay? And ideally, if you look at R square formula, right, coming from correlation coefficient, it's very easy, right? Given that R can be positive, negative, so correlation coefficient, rho or, R, right, it can be positive or negative. And if you look at the formula, it says covariance of x comma y. There are two values, and then you will do it, sigma x and sigma y. Okay, I'll explain. But what is correlation? Correlation shows the relationship between two variable x and y, and the relationship can be positive or negative, depends on the example. For example, if you remember in the first session, I was talking about the tomatoes price drastically increased, right? It's a real world scenario that happened in India at least. And then government swung into action, they imported quite a lot of tomatoes and control the price. So if you remember, the demand is related to supply is related to the price. Suppose if you have a higher supply of anything, I'll reiterate that example. So let's say in this case, this commodity is what? Supply for tomato is high. Tell me what will happen if the supply for tomato is high, right? Price will be what? Really low. Like suppose you have a lot of tomatoes, right? Price will fall down. On contrary, right? If the tomato supply drastically goes down, it is really low, then price will shoot it up. Agree? And that exactly happened. So there's an inverse relationship between supply and price. You can take a simple example of the metal gold. So gold supply is really less. If the gold is as abundant as iron, right, your gold prices would not have been like 60,000 per 10 gram, right? If you already are aware of these things in India, right? So it has to be have a relationship between any two variable. You can map it with this formula which says find the relationship of spread of data between 2 and x and y, which is your covariance, and then normalize it with the standard deviation of x and the y. Okay, but this is a formula which actually, if you break it, it will look mathematically this. So I'll say mathematically. So generally, when we run a full program, we actually go and derive this formula as well, my dear, right? So here, if you see, I'm just giving you the formula, which is you will subtract the mean for x, right? And do the product of yi minus y bar, right? I equal to 1 to n, and then sum it. So you're doing actually, uh, deviation from the mean for the x and deviation. So you're what you're doing? Sum of product or deviations of mean of x and y's, right? And then what you will do, you will calculate the variance, which is, you already know the maths, right? I equal to 1 to n. This is for, uh, right? This is for your variance is what? Then you have to also divide by n, but for the time being, guys, since n and n will cancel each other, so this will become your variance. And if you take root, it will become standard deviation, guys. So I know it doesn't look uh, clean. Let me do it a little clean. I'll use some different color. Yeah, makes sense. And I'll use different color for this guy. I'll write. See. Cool. Comfortable. So this is the formula which you will be using to calculate, and which I'll demonstrate all of it, right? I'll demonstrate all of it for correlation coefficient. Now, correlation coefficient can be 0, can be perfectly 1, can be, excuse me, can be perfectly -1. Perfectly 1 means, you have a perfect, strong, positive relationship. Perfectly -1 is like what? Uh, -1 is perfectly, negative relationship, but strong, right? And when I say perfectly strong means like 100%, right? Strong means just close to 1 or close to -1. Strong and weak are the two different things, right? So let me rather than confusing you guys, if I can give a quick summary of it, that will be very helpful for us to go through and understand. Okay, so generally these are tongue twister. You can get confused. So let me show you on the screen and explain. If you take r equal to, start with 0, the last line, then there's no linear relationship between x and y. That's number 1 point. If r equal to 1, then it's a perfect positive linear relationship. Okay. And if r equal to -1, it is perfect negative linear relationship. So how does visually it will look like? So there's a very nice image, and thanks to the guys who have put together these infographics. If you see there, right? So nice charts they have put together. Look at that perfect positive relationship. If you increase x, y increases. Can you feel it, guys? See, if you increase x, y increases on the graph. See, and all the data points are on the line. That's important to be observed, right? Second thing, I'll go to the perfect negative correlation, right? If you look at here, this is x, this is y. If you increase x, observe, as you go from, higher x, y comes down. Can you observe that? See, y is coming down. But again, here it is -1. It means that perfect negative relationship, right? So basically, it means that all the data points will be still on the line, but it is now declining trend, in, upward trend and a downward trend. And when you don't find any trend, can you see that in this middle example, you don't see any trend. It's like all, randomly distributed. Here, there is no relation, right? So when there is no relation, uh, so then you cannot actually come out or get your model to do something about it. It's more like x and y are not they're independent, right? They're not related in any way. A lot of time, I would like to caution my dear learners that people think that correlation is causality. So that's a food for thought. Correlation is causality. So there are two words. Correlation I've explained. Causality you have to work on it. Generally, when we run the when we take sessions in our typical gate paper session, right, DA paper session, we have a like a dedicated 30 minutes of discussion on that. That correlation doesn't lead to causality. So the answer is not correlation means causality, right? Actually, correlation is not equivalent to causality. Let me just update it. This is something what you can do. I'll give as a self read for you. You can just do a little bit of research around it, and please share some examples in the chat where please share examples in the chat where you can take and there's a very good example available, right, where you have a correlation, higher correlation between x and y, but x and y are not even related. You understand what I'm saying? Means you find that there is some correlation between x and y, but it doesn't lead to any causality. You understand? Since these two are related doesn't mean that this is causing it, right? So it doesn't lead to causality. So if you and even the future learners who will be coming and visiting this page and watching this lecture sometime, I don't know, today, maybe after a month, please make sure that you share your thoughts in the chat, and time to time I'll keep coming and interacting with you guys. So you can always ask me a question under the chat, right? And in the chat I can come back and answer some of your question. Okay, that way we can be still be connected. Make sense? Now I can show you some like a bouquet of examples. I'm taking one more good screenshot, guys. So you have seen 100% positive -1, but look at this. There can be a strong positive correlation, r equal to zero point 0.7. So it's not 100%, which is perfect, but you can see that it shows you a graph. And GATE generally, I expect will ask question that it is strong positive correlation, right? Here, if you see R is zero point 0.3, so that goes into the category of weak positive correlation. It's not very strong. Can you see that the data points, actual data points, are far away from the, excuse me, regression line? And you already know that this means no correlation. I'll update it. So this is no correlation. And on the bottom, you can see we have written, you know, R equal to minus zero point 0.7. So you can see that it is a, so all these are like upward trend if you've observed, right? These are, downward trend. As X increases, Y decreases. So this will be known as strong negative correlation. Negative correlation. R means correlation, guys. This means, look at that. This means weak. Why? Because zero point 0.3 is weak, right? So weak negative correlation. And again, this is the same chart. It means no correlation. Are we clear, guys, on this? Any question? Mhm. So, guys, then we have a formula for, shorthand formula. I was telling, right? I'll also give you some shorthand notation formula. So please take it, note it down. This is known as shorthand notation or shorthand formula for linear regression. I'll quickly give you. And in the next session, we are going to show you example using Excel, and that will be the last session to conclude linear regression and interpret the results. So guys, if you remember, I had given the formula for alpha equal to, y bar minus bx bar, right? This is a shorthand notation for alpha. If you observed, I would have written, similar to that. Beta is something I've written a long formula, but now you can write it covariance of x comma y and variance of x. This will also work. What we can do, we can try to use it and see that if does it make sense. Now, r square can be written as r. Already we know the r. What is r? R is what? Covariance of x comma y and sigma x and sigma y, right, guys? And what is r square? Sorry about the throat. It is s square xy and ssx and ssy. Now, this is something very new for you. And let me give you the idea about it in last 2 minutes. So guys, if you see here, sum of square deviation we already know, right? So when we say SXX, this means sum of square deviations of x's from their mean. So basically we are saying it is variance of x, right? And you are multiplying with n minus 1. That multiplicative factor can be anything else. It can be n or n minus 1. But when you are talking about sample, it will be degree of freedom is n minus 1. So we'll use that. SSY, similarly, it will be equal to n minus 1 variance of y. And let me give you the last one, which is sum of square between x and y is equal to what, guys? N minus 1 covariance of x comma y. Cool. So these are the ones which you have to keep in your head. And if you really want to get a detailed understanding of it, that's where I would again like to reiterate my comment. We are running a GATE program session, and I hope if you are liking or enjoying these sessions under the master series for simple linear regression, make a point to click on the link. And where you will find the link, guys? Link is present here under the description. So I'm showing a screenshot. So if you see in the YouTube app, in the description you will find that there is a link for online program. For classroom program you have another link. So whatever suits you, you can find the more information clicking on this link, and all the notes of this lecture will be shared in this particular Telegram link, right? So you can join this and be informed about the recent updates or changes we are doing. Make sense? Cool. So any quick question, guys, on what we have covered so far? If not, give me a thumbs up and stay tuned to the channel. Keep supporting us. Like, subscribe. This is important for us to function. Okay. And those who have been watching my session for the very first time, those who have joined this for the first time, so I'll quickly introduce myself. Generally I do in the beginning, but today I was trying to get into the topic. So my name is Akash Pushkar. You can call me APC. I'm a IIT Kanpur alumnus, currently working as a lead data scientist with Accenture Statin Consulting. I have trained more than 30,000 people, okay, in GATE student for the last few years, and I think that will be spanning about almost a decade, and 15 plus years of experience in training and mentoring. I have a very subtle position of doing data science and the GATE, and that's where I'm teaching some of the students on preparing them and getting them ready for 2024 GATE DA paper. If you're interested, as I've highlighted, you can always click on the link and get more information about it. So thank you very much, guys. Take care.